Thanks, Emilion. And yeah, it's absolutely great to see you again, Seba. And thank you to all the organizers for this. It's absolutely brilliant. And I'm delighted that you invited me, and delighted that I'm opening this. So I'll keep this at a high level. There won't be much math or stressful stuff, so that you can really believe that you are on the beach at the moment. Maybe some of you are on the beach because there's 150 people in this call, so maybe some of you is actually on the beach. Um, I'll try to keep on time. So give me a warning if I go too long. I could talk for a long time. So my title is broad in that it gives you the idea that my work is about auditory cognition, of course, and specifically about speech and music, which I take as two different angles to understand the same type of processes. And this is my team here. So since I sometimes forget, I'll just start by thanking my mentors on the top left and my team on the top right, and then the work I present is from a good few collaborators and funding agencies. So the first point here is, okay, how do we understand speech? How do we transform speech into meaning, right? So that's the big question that I'm interested in. And traditionally, when we talk about neurophysiology, one approach to study how speech is processed by the brain is, for example, to use event-related potentials with paradigms that basically involve presenting simple sounds to participants while we record electrical activity. So, and then we just take these chunks of EEG activity. It's the same for MEG or other technologies, and we just average them, obtaining this so-called event-related potential. This approach requires simplification. So you need to work with syllables, with individual words, or have a particular target word, or so on. I'm interested in more realistic experiments. So we learned a lot from this type of discrete paradigms, but I was interested initially, and I'm still interested in understanding what we can learn from basically playing to participants natural speech from audiobooks or more naturalistic, more ecologically valid stimuli. So my initial question was quite methodological, and I'll go into theory in a second. So one of the issues with syllables, for example, is that when we listen to a syllable might be embedded into different words. And so the sound in probability or bat, so the ba in probability or bat is going to sound a little bit different. So context is going to change the instantiation of that syllable. Same thing at the semantic level. The word bank might have multiple meanings, and so context is going to matter. So my kind of experiments involve basically listening to pre-recorded speech as participants, as I record the neural activity from participants with, for example, non-invasive EEG. On the left, you have a biosemi system. We also use this mobile system from M-Brain Train. And now we have a new OPM MEG system that we are about to test. So the assumption is the same as in the ERP world. So the assumption is that you have a neural signal which is mostly garbage because it's mostly noise. But behind that noise, there is something good. And that something good is going to be, for example, a response to the sound, a response to the phonemes, a response to the syllables, and so on. And so we can take this onion, this linguistic onion, and we can imagine that, okay, maybe someone wants to study syntax. Jonathan Brandman studies syntax, for example, and you assume that that's encoded somewhere, and you try to isolate that. With models that vary in complexity. So my approach involves extracting features from the speech, often with nonlinear transformations, and then relating those features with EEG using models that are linear. So we use these linear models because a linear model is more interpretable, and also for other reasons that I won't explain now. But basically, all the nonlinear complexities in this feature extraction, and then we try to figure out how much of a feature is encoded in the EEG. And then we can use that feature, that metric, to study the processing of that feature, and so on and so forth. To do that, I use a number of tools. One of the main tools I use is the MTRF toolbox, which I'm an author as well. And one of the things I did was to take this method and work towards the evaluation and standardization of that kind of data sets. So I won't stay on this slide very particularly long, because this is somewhat of a hidden advertisement of another event, which is not good to do. But basically, this is an open science initiative that is specific to the kind of data that I collect and that I use. And so we have lots of resources, data sets, and code. So I tend to share every type of data set that I collect and code. So the idea is, we take these features, which are, for example, the spectrum of the speech, the phoneme categories. Then there is a type of feature which is expectation. So how expected is a phoneme, or how expected is a word given a particular context. So we'll see a few of these in a second. And then we relate these with EEG. Basically, the metrics that we get indicate how much variance, how much of the EEG variance we can explain from a given feature. So basically, if phoneme categories are encoded, they should explain some unique variance in the data. So very statistical approach. So this is an early work from my PhD with Ed Lawler. And the idea was that we played audiobooks to these native English speaker listeners. So they listened to The Old Man and the Sea by Ernest Hemingway. And then they listened to The Old Man and the Sea that was time reversed. So it sounds like, sounds terrible. So you can't really get words, you can't really get phonemes. So not reliably anyway. And so what you see in orange here is the unique variance captured by a phonetic feature, by phonetic features in the EEG. So there is some phonological encoding here for natural speech, but not for time reversed. And then we can get these model weights. So the model that we use, they are linear regression models. And so we can look inside the actual model. And we can see that there is, on the x-axis, the time latency. So 0 is when you hear sound, and red and blue represents basically positive and negative deflections of the electrical response. And so basically, consonants and vowels give you different patterns. And so far, it's basically a colorful picture. Can we do something with that? So the rationale, and here comes a bit of the theoretical question, is that there is quite a bit of evidence on the fact that our brain might be encoding phonemes in a categorical manner. Not everyone agrees, but there is evidence that points in that direction. Lots of that evidence comes from this discrete type of experiments where people listen to individual syllables. And so one of the concerns is, okay, we are listening to Ba in different types of acoustic versions, and does our brain encode that as a category somewhere? And if we measure that with discrete paradigms, does that mean that generalizes to realistic continuous speech listening? So it's not that trivial. Other people don't believe in phonemes at all. And here there is a reference to that. It's not exactly my view, but it's fair to look at all sides. So my point was, basically with this method, maybe we captured categorical phonological encoding. But are we really? And after I published that paper, there were other papers that were discussing and potential issues and so on. And Christophe Daub here had a very good point to discuss. He's a very nice guy, even though we disagree on that point. So there are some colleagues that went for an explicit validation of this study from my current biology 2015. So I wasn't involved in these studies on the yellow box. These are just other colleagues doing their own work, and some of them did an explicit validation. In this case, is with intracranial data and 2 languages. And basically, the whole paper, or a good part of the paper, serves as a validation of that study, which was very rewarding to see, because I wasn't even aware they were doing that. Then there are other people that did their own work, and as they were doing their work, they also provided some insights that somewhat validate this idea of phonological metrics with EEG and continuous speech. With different languages as well, so it was Flemish, German, and French. This was English, I think, and then Italian. That's the latest one. So again, very rewarding. What I have been doing instead is a bit different because I've been applying these phonological metrics, EEG metrics of phonological processing to different cohorts and different tasks. So I'll show you this list in the next few slides, basically. So I've been working with infants, with second language learning, with children and dyslexia, and other tasks like attention switching and looking into different speech registers. So there is quite a bit of work. So I'll just do a quick overview, basically to make the point that all these metrics really capture phonological processing. So one thing that we expect from babies, for example, is that phonological processing emerges at some point in their first year of life. They don't speak usually in their first year of life, so it's very hard to test in other ways. There are tasks that we can do, but they're very, very hard, very simplified. So we basically played nursery rhymes to infants, and this is a longitudinal cohort of 50 infants recorded, each of them recorded 3 times at 4, 7, and 11 months of age. So we have 150 sessions in total, and this was recorded by Professor Usha Goswami's group in Cambridge. So I've been working with Professor Goswami for a number of years, and we managed to combine this analysis with our data collection. Basically, the first result is that if we look at how strong the brain of these infants encode sound, that's what this picture shows. This is topography, so the top of the picture is the nose. So this is basically a picture of the head seen from the top. And basically 4, 7, 11 months of age, they process sounds, right? If they hear, they process sounds. So it's not surprising. But when we talk about language, so in this case, phonological encoding, we see an emergence of this phonological encoding from 7 months of age that you can see from these topographies, and you can see in this line plot on the right-hand side of the slide. And you also see a data point which is for adults, because we had an adult control here. So this is practically where this encoding will culminate. But consider that these 3 are the same participants, the same children that grow older. So we got really excited because this is not different from what the literature showed before, right? It's not, Patricia Kuhl has been talking about this for years. And it's just beautiful to see this with continuous speech. And it was not obvious that this would be the case. So we did more analysis in that paper that I don't have the time to describe. I'll fly through this because I want to get to the music part. So we did basically the same method. We applied the same method to second language learners. So these were Mandarin speakers that were learning English. So we have 52 second language learners at different levels of proficiency, and 22 native English speakers. Now the result is, again, it's trivial in that the higher proficiency level should have a higher phonological encoding. But the metric that we use to show that is definitely non-trivial. So we take these maps, the phonological maps that I showed you before, and we project them onto this PCA space. It's a multidimensional scaling. And then we use an analysis that is called Procrustes to map the second language speakers with the native speakers. So we're basically trying to see how similar the second language speakers are to the non-native, to the native speakers. And I'm sorry that you can't see my Italian hands that move and point at the slides, because there is a lot of movement that is happening behind the camera here. So, so you see the red data points here, they are phonemes. It's the neural encoding of these phonemes for the non-native speakers. And basically the point is that, okay, you have consonants on the right, vowels on the left, and nasals a bit there on the bottom. But the red and the blue, they're not that similar, and their distance is quantified by this bar. And then we move to intermediate speakers and to advanced speakers. So I show you all 3 of them at the same time. So you see basically the 3 maps are getting more similar. So participants that have a higher proficiency level in English, they have a phonological encoding that is more similar to the native speakers. So the result in itself is, I think it's obvious. You're to a certain point, because of course there are questions on whether you converge to the language fully, or the impact of your native language. But the fact that it improves, it's obvious. But this is a validation of this metric to say, I think we're really capturing phonological encoding, and we don't see that. We don't see a progression of that kind on the acoustic encoding. So this combines the adult learners and the infant data to show that basically as they become older or as the proficiency increases, the phonological encoding becomes more similar to the adult native English speaker. And there is more work that I've been doing with Giorgio Piazza, for example, is joining my team as a Marie Curie fellow in November. And he has been looking to speech register. And short story short, if you speak to a non-native speaker with something called foreign directed speech, so you talk to me knowing that I'm a foreigner and you talk to me in a simplified way, acoustically, that actually helps me, but doesn't help a native English speaker. So we have all of these balanced data sets, and to validate, basically, ultimately, we're validating this metric. And so the take-home message here is we have these metrics. I think there is overwhelming evidence now that we are capturing phonological encoding, and that these acoustic metrics instead don't show this progression in language encoding in this type of models. So it's really nice to be able to disentangle these two processes. Now, this is my little contribution to the field. And this contribution is on the area of, okay, what does our brain actually encode? And maybe, at what frequency does it encode a particular feature and so on. Other colleagues have been looking into where things are encoded, and even trying to do decoding and building brain-computer interfaces that used to sound like a dream, but now they're getting really, really exciting, really, really viable, invasively, typically. And my conclusion here, my take-home message is, I think running these continuous speech experiments is actually a valuable approach. And so this is the transition that we are experiencing. So this is a work I've been doing with my student Emily Ip, where we are reviewing a little bit the field. So going from syllabus to audiobooks, the next transition that is already happening is, instead of playing pre-recorded sounds, is going towards more interactive scenarios. And so going to, real dialogue between two different people or groups of people. And so that's something that is happening right now. And I find that direction fascinating. And, there are lots of new challenges and opportunities when we study interaction with these methods, because now we have adaptation, we have anxiety, we have trust and humor that become more relevant than what they could be with an audiobook, let's say. I skip this because I don't have enough time. Some of that work, by the way, I gave a talk last week at a conference called Cog Here, and I go a little bit more in depth on that part on a video that is on YouTube. So, but I prefer to talk about something different now, still related, but using a different type of stimulus. So music. I am interested in music in general, but also as a stimulus that looks at auditory perception from different angle. Now, the beauty of music, from my perspective as well, for these kind of experiments, is that music has to be continuous, has to be, a continuous stream. And if you play simple melodies, it's okay, but they don't sound amazing. While instead, if you play everything together, it sounds beautiful. So for studying music, we really need to learn how to work with these more realistic stimuli, more complex stimuli. So these are some topics that I'm interested in. I'll just present a couple of them. So let me start with a study from 2020, where basically I was replicating some of the work that we had done with speech. So participants listened to, in this case, melodies, piano melodies. So are synthesized artificially. This is not improvised or anything. So this is the score, and you have the envelope here, the acoustic envelope. And then we took this model called Idiom. Marcus Pierce was the author of that. And now we're using different model. We're using a music transformer, which is basically a GPT of music, which is a bit more richer in content, in training data. So what these models can tell us is basically, given a note and the preceding notes, it tells us how surprising that note is. So it gives us some metrics on the expectation of a particular note at a particular time. So in this experiment, we had 20 non-musicians that were listening to, 20 participants, 10 were non-musicians and 10 were expert pianists. And then there is data from 3 non-musicians that were recorded with intracranial data from Nima Mesgarani's group in Columbia University. So the idea was that if we take our model with acoustic features and we add on top of this these expectation features, our brain should reflect these surprises, these expectations, because our brain detects the context, and as a consequence, is going to be more or less surprised, engaged. We can talk about predictive coding there as well. We are going to get some unique variant that reflects this expectation. That's the take-home message. That's what we measure with EEG and with intracranial data as well. So these increases are tiny. So these numbers are very small, but they're really reliable. So this is single subject data on EEG. And so you see the blue versus the orange is this is what we're looking at. So there is this increase for basically every subject. So small numbers, but really robust, that tell us, okay, we pinpointed an area of the cortex that is sensitive to melodic expectations. And we found that this was actually in secondary areas of the cortex, so in planum temporal, but we didn't find any of this expectation response in primary Hashler's gyrus cortical areas. This was replicated by other labs independently. And also, Roberto Bianco recently had a current biology paper on monkeys, where they showed that monkeys can, basically, they also track these expectations, but just the rhythm expectations and not the pitch variations. And she has some new work on babies as well, I think. So my question here was on polyphonic music. Talking about moving towards more naturalistic, it's just one step beyond. It's still a very particular type of music. This is double counterpoint music. It's a particular type of music with 2 streams. This is piano. There is a high-pitch stream and a low-pitch stream. So this is work that I described is from a student in my team, Martin Winchester. So, and others as well. So the idea of this double counterpoint is that basically with very few musical ideas, you can jumble things around in many ways, and you can get many different variations, and they all sound good. I'm really simplifying here, but that's one of the points of double counterpoint. So you see here, there are different hypotheses on how our brains might be processing these 2 streams. For example, it might be merging these things somehow. It might be processing them separately as 2 independent streams, which is a bit weird because music, the 2 streams are going to be related. Or maybe you process one stream as the main melody, and then the rest becomes processed in function of that. And that's called the figure ground model. And then there is an integration perspective, an attention switching perspective that said that you swap between one and the other, and another is an integration perspective. So this is the first time that I present this data, so I'm really excited. So we had a main condition in this study to basically try to figure out what model really reflects how our brain processes music. So we played this polyphonic counterpoint type of stimuli. We've also played the monophonic tracks. So we took the high pitch, the low pitch, etc., and we played them by themselves. And also we inverted the high pitch and the low pitch so that the support stream suddenly became the high pitch stream. And I'll show you in a second why. We had a behavioral task where we asked people, what is the high pitch stream? What is the melody? What is the main melody in this particular segment? And so we obtained the behavioral attention bias metric. And from the EEG, the goal was to get a neural attention bias metric, basically to understand where does the attention go during uninstructed listening of polyphonic music. So we had three hypotheses. So for the original, the hypothesis was obvious. Participants primarily pay attention to the high-pitched stream. That's how things are usually when we listen to music. Not always, but it's usually like that. And definitely with these pieces. And then we had three hypotheses that when we invert the streams, we still pay attention to the high pitch, we pay attention to the low pitch stream, or we are kind of in between. And the reason is that our auditory system is biased towards is attracted by the high pitch streams, and that's called a high pitch superiority theory or effect, high pitch superiority effect. But also the high pitch is usually loaded with more melodic components. It's more interesting. And so when you invert them, you suddenly have the more interesting stream in the low pitch, but the high frequencies are still attracting you. So we didn't know what would happen there. And behavioral and EEG results, they match. They both show that, okay, people pay attention to the high pitch in the original version. When we invert, instead, there is a reduction in that bias towards the high pitch. And we use EEG for detecting basically where the attention goes. But and this is the final bit of this study. What we saw that was really exciting was that when we take GPT, it's not GPT, it's a music transformer. I just call it GPT because everyone knows what GPT is. When we take this transformer, this GPT style music model, so we took two models. One model that treats the music as monophonic, as if it was just one stream at a time. And instead, another GPT that merges the two streams, and so treats them as polyphonic music. And we wanted to see which model matches the data best. So in the original condition, in the original stream where there was a bias, clear bias toward the high pitch, basically the high pitch stream is processed as the melody, and the monophonic model is the winner. But when we invert the model and the attention is somewhat in between the two, the winner, the best model is not the monophonic model anymore, but it's the model that proposes an integration of the two streams. So this gives us quite a different picture from the single hypothesis perspective that we had before, right? Because it might be that when the attention is really biased on one side, we process things in one way. And when the attention is in between, maybe we're really truly integrating the streams. And that's something that we need to look into more in detail. Just one other minute for one slide, and then I have the conclusions. Generally I don't say we are scared of complex stimuli, but, stimuli with lots of components, lots of factors, they're problematic when we want to test particular effects, but sometimes they're useful. So in this case, I'm very excited of this study because basically we got participants to listen to sung speech, just a person singing. And then we had a version of that sung speech that was just the person humming that song. So we have a melody version that is just melody, and a song version that is melody and language. And this transformation was done computationally, so the timing was exactly the same, and the envelope was basically the same. So when we look at the two conditions, melody and song, these are again topographies. You see they're fairly similar. For song, there was a bit more stronger encoding, maybe because it's more interesting. Nothing shocking here. When we look at melodic surprise, which is the same metric from the previous slides, this is the first time in 12 plus years that I see a lateralization so clear anyway in EEG. It's actually significant and robust across participants. Usually when we play melody, we just see responses that are so central, right? But when we have this stimulus that is melody and speech together, melody and language together, we start seeing lateralization. And when we look at the same data for studying phonemic processing, we see it on the other side. Now, people talked about lateralization for years, and I'm not against that, right? I think it's just a good lesson that I learned, that maybe when we just look at speech by itself or melody by itself, it's not enough challenge for our cortex, because both cortices can get involved in speech and music, and when we force them to pick one, then we start seeing this lateralization effect. So complex might be good in this case. So just to conclude, I think going back to the start of the talk, in my view, there is overwhelming evidence that we have a categorical phonological processing that can be measured with non-invasive EEG, MEG, and continuous speech stimuli. I'm aware that some colleagues don't want to agree with this, but I've seen it in so many different ways that I can't see the problem anymore. In children and second language processing. We saw it also, I didn't show the slide, but also in dyslexia. So these metrics are also sensitive to the phonological deficit in dyslexia. And there is more. And similar results have been found on predictive processing, and that's one line of research I'm following for going towards more naturalistic, socially relevant scenarios. And finally, melodic prediction can also be measured using music streams or continuous music. We saw that attention can potentially might be changing the way we integrate, or whether we integrate these streams when processing their context and their expectations and so on. And finally, complex stimuli can be an advantage. So let's not be scared. We just need to be really careful and have proper controls. So I conclude again with my acknowledgement slide, and thank you all for 190 people for listening to this. Thanks.
Giovanni, thank you very, very much. It was awesome presentation. A lot of things to discuss here. We're going to go directly and cut the cake here and shoot a couple questions. So virtually, they all applaud you, I'm sure. So thank you again. It was very insightful, and I love how you embrace the very complex stimuli, as you said, which is a good message to share. So I will start right away with a couple questions that we have from the audience. The first one that I see here, it asks, is there any known regression of phonological encoding ability evident from EEG due to age-related degeneration and/or hearing loss?
I think that's a brilliant question. That is really a brilliant question. So I have one study on hearing impairment where participants had a hearing aid for the experiment, so there was compensation. Of course, compensation is not going to bring them back to normal hearing. So in that case, it was more of an attention study in that case, and the take-home message was that we saw an increased encoding of the phoneme onset in that cohort, and almost an inability to suppress the phoneme onset of the unattended stream. So that's a typical question in hearing impairment, because the difficulty is especially in noisy environments. Now, one interesting thing is that we had difficulty measuring phonological processing in that cohort. So I am not aware now of studies that look specifically into your question. I don't know. I think it's a very hard question to answer because there are so many consequences of the hearing impairment. But if I can speculate, I would imagine that there is some, but there is a bit of everything, and so it might be really hard to tease apart and to be conclusive on that. But it is a very good and very important question. Jonathan Simon has been working on aging quite a bit and looking into vowels and consonants and coding. I'm not sure if he looked into that level of detail, but that's a great question. Thanks a million.
So this is important, I guess, from a lot of people in the audience, since they're working with hearing loss people and everything. So they're looking forward for your coming studies in the topic. I have a second one here that we'll just go for, which is, what's the music not already familiar to listeners? How to ensure people hadn't already encountered Bach's music in daily life?
Mm-hmm. So this is another beautiful question. So our first concern was whether we could measure this at all. And so we didn't worry too much about that. And of course, prior exposure would change your expectations. The model that we were using actually incorporates this short-term expectation versus long-term model. So basically, you can disentangle the part of the expectations that is due to familiarity versus the part of the expectation that is due to the more local context. So there are two different types of prediction. And in predictive coding or predictive processing, it's not necessarily the case that the surprise goes down to zero, right? Because even though you have heard that before, there is still a chance that you hear something different. So in that case, we controlled for familiarity. We had a simple subjective report on that. We were in the first experiment, the eLife paper, 2020, we were asking them, and they were rather unfamiliar with that material because we picked pieces that to regular individuals that are not into music that much, they were not that familiar. The musicians, yes, there was more familiarity there. So it is potentially a factor. On the polyphonic music, no, they weren't really familiar with those pieces because they weren't as common as you would think.
Nice.
But it's a very important factor, and for polyphonic music, I would think it would actually change the way you process it would change where the attention goes.
Nice, interesting. So I don't see any more questions, so I will shoot one last question from my end. You mentioned this bilingualism, which is important in many aspects, and in a city like Miami, where even my kids talk to me half and half, Miami style Spanish and English all day long. I wonder a couple things around that. First, if you measure other language besides the one that you measured, because each language has its own feature type of thing, and if that plays a big role. And just briefly, another thing is the perception that you're measuring also related to the production that they do. Like they perceive very well maybe every phoneme and everything, but do they speak the language as good as they perceive it? Are you measuring that as well?
Mm-hmm. Now that's another. You keep asking me very good questions, so that's great. So on the languages, yes. Other colleagues have studied Flemish, German, Italian. So this is Lars Meyer. He did a study with German, and the French was the control, and there was Flemish from Tom Franker's group, and Italian Alessandra Federici. And she's studying cochlear implant, by the way, cochlear implant implanted children, and that was really. I'm really delighted that they're doing that. So there is going to be some results, some interesting results from that team soon. They have a paper, but not on the phoneme part that will come. That was the first part. So yeah, there has been people trying to this with different languages, and in some cases it works. It's not that trivial because of course there might be languages where things are just so inconsistent. So you still need in aligner, a phoneme aligner that works, that is reliable, because if the aligner, if you don't know where the phoneme starts, if there is no way to know where the phoneme starts, then it's tricky. Your other question was, I'm sorry, could you repeat it?
The perception and production relationship.
Yeah. Sorry. That's another good point. I haven't, these studies I've shown, I don't have that.
Mm-hmm.
It is something that we have been considering. So there is a study with Professor Usha Goswami on production in children with dyslexia, for example, and also developmental language deficit, where basically they do a listen and repeat task. And the hypothesis there, or at least my understanding, is that because their perception is different in terms of phonological awareness, when they produce in a simple listen and repeat task, the envelope and the F0 are going to change in an almost imperceptible way, for us, that for when we communicate with them. But if you measure it, you actually see on the production a difference. So on the dyslexia, I don't have it on these cohorts, on the particular sample that where I have the EEG, but we have been looking into production as well. And now Martin Winchester, which is also the student that is looking into polyphonic music, he's working on EEG metrics of production, which are really hard to get. And so we're doing our best to try to get that as well.
Well, so much to keep discussing here, but for the sake of time, I think we will just give you the very big thank you, Giovanni. You have inspired us and opened our brains a little bit in